Next question I would like to ask is, which department do you belong to? Are all of you in physics, or we have some other guests? So you're all in physics. In previous years, we had some students from other departments as well. And the last question for now. What do you expect to get out of this workshop? Knowledge, experience. Writing skills. Such tools. Good. All right. Let's go back to our PowerPoint. So the syllabus for the class, we are going to go over today and our next meeting on the 21st on the scientific method, peer review, replication crisis, open science, and beyond. The next session will be about how to write and critically read a good paper. We'll analyze as an example the famous Watson and Crick paper on the structure of DNA. Then I will describe a Forster paper, fluorescence resonance energy transfer, and talk a little bit about my own research using single molecule spectroscopy to look at dynamic structure in proteins. And you'll get a home assignment after this lecture. And then we'll dedicate the last two meetings for scientific fraud and misconduct. So when we talk about what you expect from this course, it's really about how to do science right or how not to do the wrong science. We'll have many examples. And for the last four meetings in this quarter, in this semester, you are going to actually present. So the first 6 classes, I'm going to give you frontal presentations using PowerPoint and Mentimeter. And for the last 4 meetings, you are going to have each a PowerPoint presentation about 25 minutes long. You will have to pick up a topic and consult with me to get my authorization for this topic. We are mostly looking for famous cases where there was scientific fraud or misconduct, papers were retracted, and so on. You'll see the examples when I give some examples, but basically that's what we expect you to do. You'll have to present a PowerPoint presentation in English to the whole class. Participation is, especially for that last part where you talk to your peers, I expect everybody to be present. We will not allow more than one time that you don't show up. So make an effort to show up for this class. Any questions so far? If you do, please turn on your mic and ask questions. No questions. Okay, let's move on. So this is a pass-fail course. Nonetheless, pass means 80%, fail is anything below 80%. So this is how we are breaking down the grade. Participation is 15%. Home assignment, there will be 1 home assignment. The deadline for this home assignment will be June 16 at midnight. That's 20%. The next two assignments are basically similar. You're going to pick up basically a paper that you're going to present. You are going to prepare a PowerPoint and present that PowerPoint in the lecture. You are also going to write 2 pages, a PDF document that summarizes your talk. So the deadline for the 2-page PDF is June 30. That will be 40% of the grade, and the last part is your presentation, which is 25%. And you have to send me your PowerPoint before giving the lecture. So we are meeting on Tuesdays. By Sunday before your lecture, midnight, you send me your PowerPoint. Any questions about that part? Okay. Okay, so just as help for preparing your work, here is some reference. When you write your PowerPoint and you write your 2-page PDF, there are many resources online that you can find. Here is one link, how to write a peer review. And for PowerPoint presentation, what we expect you to do is to tell us a good story, mostly about misconduct, bad paper, retraction. It actually can also be an example of a very good paper, but you'll have to work harder to try to convince us why it's such a good paper. Okay. Any questions? All right, if no questions so far, let's start. What we are going to cover today is the scientific method, the peer review, the failure of the scientific method, and this might be a surprise for you, but in the last 2 decades, more or less, we have been experiencing a crisis. It's called the replication crisis, and we'll describe what this is all about. The response for the replication crisis, and you might have been experiencing already something called open science, and what goes beyond open science. So let's start with the scientific method. So use your own words. Please tell me what you think constitute the scientific method. Review, limited theories, fact checking. What do you mean by today? Turn on the mic, whoever answered that question. Fact checking.
It was a type of study.
Oh, study. Okay. Creativity and criticism. All right. Review gets higher weight. Anything else? Okay. Based on experiments. Good. Okay, so let's go to Wikipedia. The scientific method basically requires careful observation, formulating an hypothesis, experimental and measurement-based testing of deductions drawn from the hypothesis, refinement or elimination of the hypothesis based on the experimental finding. The scientific method is basically the process which science is carried out, as in other areas of inquiry. Science, through the scientific method, can build on previous knowledge and develop more sophisticated understanding of its topic of study over time. And basically, the idea is really to move the front of knowledge forward. So let's just have some bullet points here. Yes, go ahead.
I just want to ask the previous definition. Wouldn't that exclude mathematics?
No, it doesn't. Well, let's go through this list and then we can maybe answer your question better. So the first step is to formulate a question, and this is based on accumulated knowledge. Come up with an hypothesis, prediction, testing. So testing could be experimental, but it doesn't have to be. Testing could be simulations, for example. Use appropriate method, control experiments, or control simulation. Analysis of the experiment or the simulation or whatever you've done. Replication and retesting. External review, and that came up in your responses. Data recording and sharing, and that's relatively new. Until about 30 years ago, we did not used to do this. So nowadays we have depositories and so on. We'll talk about this, but this is basically a response to the replication crisis. Publication. And once we accumulated and advanced the front of knowledge a little bit forward, we come up with the next question. So science is basically very iterative, progressive. We basically iterate and advance our knowledge piece by piece. Very few revolutions. It's mostly evolution. But basically, we build a hypothesis, we test those hypotheses, we advance the knowledge, and then we ask new questions. So as an example for a good paper, good progress in the scientific front is the double helix example. The history of the discovery of the structure of DNA is a classic example of elements of the scientific method. In 1950, it was known that genetic inheritance had a mathematical description, starting with studies of Mendel. It was clear that DNA contains genetic information, especially after Oswald Avery's transforming principle. He did some experiments that really proved that DNA carries the genetic code. But the mechanism of sorting genetic information in genes in DNA was unclear. Researchers at the Bragg laboratory in Cambridge made X-ray diffraction pictures of various molecules, starting with crystals of salts, proceeding to more complicated substances. And at some point, they started to play with crystals of DNA. Using clues painstakingly assembled over decades, beginning with its chemical composition, it was determined that it should be possible to characterize the physical structure of DNA. An X-ray image would be the most appropriate tool. So here comes the hypothesis. Until now, we discussed about what was known previously to Watson and Crick. Linus Pauling, who was at Caltech at that time, proposed that DNA might be a triple helix. He made an hypothesis. This hypothesis was also considered by Crick and Watson, but discarded. And when Watson and Crick learned of Pauling's hypothesis, they understood from existing data that Pauling was wrong, and that Pauling would soon admit his difficulties with this structure. So a race was on to figure out what the correct structure of DNA is. So basically, Pauling was at the front of this research. He already made some hypotheses, but Pauling himself did not know really that he is in a race. Anybody knows the reason why Pauling actually missed the race? Any ideas? That's actually a nice lesson in history and very relevant to our own days. Okay, we'll touch upon this later, but this is a question I pose here. Pauling basically lost the race with Francis Crick and Watson because of politics. We'll talk about this later. So Watson and Crick and others hypothesized that DNA had a helical structure. This implied, and somebody mentioned mathematics, right? So already when they went down to interpret the work of Franklin, who did the actual X-ray diffraction, they expected to see on the X-ray diffraction image an X-shaped diffraction pattern from mathematical principles. This implied the DNA X-ray diffraction pattern would be X-shaped. This prediction followed from the work of Cochran, Crick, and Band, and independently by Stock. Those were basically mathematical works that made some predictions. They provided a theorem that provided mathematical explanation for the empirical observation that diffraction from helical structure produces X-shaped pattern. So in the first paper, Watson and Crick also noted that the double helix structure they proposed provided a simple mechanism for DNA replication. Writing in their famous paper, which we'll analyze later on in the course, it has not escaped our notice that the specific pairing we have postulated immediately suggests a possible copying mechanism for the genetic material. This is considered to be the most undermining statement in scientific history. They formulate this sentence very carefully without a big punch, although this is probably one of the most important sentences that basically started the new field of molecular biology. So Watson and Crick showed an initial and incorrect proposal for the structure of DNA to the team from King's College, that was Rosalind Franklin and Maurice Wilkins and Raymond Gosling. Franklin immediately spotted the flaws which concerned the water content in their interpretation. Later, Watson saw Franklin's detailed X-ray diffraction image, which showed an X shape, and was able to confirm the structure was helical. Here, obviously, there is a very famous historical story about Rosalind Franklin. Her data was shown to her competitors by her advisor without her consent. And nowadays, many think that she should have shared the Nobel Prize. The way she was treated by Watson and Crick was despicable. When we analyze the paper, we'll talk about this a little bit more. But this is, I mean, I think we could even qualify this historical event as scientific misconduct. That might be going a little bit too far, but basically, Franklin did not get the credit she deserved for this work. And here you see the famous photo 51. This is the X-shaped diffraction pattern from a crystal DNA. This is what Watson and Crick were looking for. That's what the mathematical model predicts. So basically, you can see that the whole paper is really following the scientific method. We make a hypothesis, we have some predictions, we go to the experiment or to simulations if you're doing a theoretical work, and we prove that the hypothesis actually holds water. And now we understand the structure of DNA, and we can make new assumptions and repeat this process again and again. The rekindled Watson and Crick model building and led to the correct structure using this information along with previously known information about DNA composition, especially the rules of base pairing by Chargaff. After considerable fruitless experimentation, being discouraged by the superior from continuing. So basically, Watson and Crick were discouraged by their superiors not to continue this line of investigation, but they insisted. And numerous false starts, Watson and Crick were able to infer the essential structure of DNA by concrete modeling of the physical shapes of nucleotides which comprise it. They were guided by the bond lengths, which had been deduced by Linus Pauling and by Rosalind Franklin X-ray diffraction images. So obviously this was a huge victory, started a whole new field, and led to the Human Genome Project and to COVID vaccination and to anything you think about immune therapy, cancer. This molecular manipulation of genetic material really starts with the structure of DNA. And we just use this example. We are going to analyze the paper later on, but I just wanted to show you that this famous paper follows the scientific method. All right, any questions so far? All right, so we went through the scientific method. The next topic is the peer review. So scholarly peer review, also known as refereeing, is the process of subjecting an author's scholarly work, research or ideas, or proposal, if you're going after funding, to the scrutiny of others who are experts in the same field before a paper describing its work is published in a journal, conference proceeding, or a book, or funding agencies decide to fund the proposed work. So you are all familiar with this concept. And we'll ask you now a question. Why peer review? Verification, validation. Check originality. Well, I think we can do ChatGPT to do that. Validation. So five of you think that the peer review is working, making sure it's real. Guys, you give way too much credit to reviewers. Okay. So you might be surprised to know, well, the peer review helps the publisher, editor-in-chief, program committee, funding agency to decide whether the work should be accepted, considered acceptable, with revisions, or rejected. And peer review is generally considered necessary to academic quality. However, peer review does not prevent publication of invalid research. And moreover, there is little evidence that peer review improves the quality of published papers. So we are all very used to the concept of peer review, but peer review does not really does the job. We oftentimes find mistakes after publication. We oftentimes retract papers. Peer review is not, most of the time, able to find fraudulent science. And many cases, peer review doesn't really find mistakes. The peer review doesn't really work. Although we all are trained to think that peer review is necessary and very important to the process, it's subject to lots of biases. And when you get a paper to read, usually you don't do the research again. You just read, and to the best of your knowledge, you decide if it's okay or not. You ask the authors to change a few things here and there. Sometimes you have, more important criticism. Nonetheless, the reviewers do the best they can. They give a lot of troubles, takes a lot of time to publish a paper nowadays. And yet the peer review doesn't prevent fraudulent science or mistakes from happening. They happen all the time. You can open any, journal like Science, Nature, PNAS, and so on. And every week you'll find retractions. Those papers were published, reviewed, accepted, published, and yet later on some mistakes are found and then the papers are retracted. So the concept that the peer review works is kind of misguided. It's not really working. And in fact, people are doing now research to really find correlates between peer review and quality of published papers. This new field is called meta-science. We'll talk about this in a few minutes. But the concept, just put it somewhere in your head that we need to take the peer review with question marks. So what is the justification for peer review? External reviewer with special expertise cannot spot mistakes or omissions. Reviewers are often anonymous and independent. There are different journals with different rules. Nowadays, we are moving more and more into what we call double-blinded review, where the reviewers don't know who the authors are, and the authors don't know who the reviewers are. And on the contrary, some journals are now require the authors to be anonymous to the reviewers, but the reviewers to be public to the authors. This is for more transparency. What is the procedure? Basically, you submit a paper to your favorite journal. The editor has what is called the desk evaluation. Is this something we are not going to consider at all or not? And then they decide on, let's say they think that the paper might be suitable for the journal. They send it to reviewers, and the review will be blind in terms of the authors don't know who the reviewers are. That's a common way of doing this. Although, as I mentioned, nowadays we see a lot of changes, and many journals now ask also the authors to be anonymous to the reviewers. Reviewers will ask for revisions from the authors. The authors will put in those revisions and submit the paper again. So as we said, peer review has different styles: anonymous or attributed, double-blinded, single-blinded, or not blinded at all. And open peer review is something that is taking hold nowadays, where basically there is no official peer review at all, except that the authors put the paper, and eLife is going in that direction. They basically post the paper, and the community basically comments on the paper over time, and the review is basically accumulating and building over time. Like what you do in social media, you are actually trying to adopt that concept into the review process. This is called open peer review. Another concept is basically pre-publication, and again, the review will come only after the paper is published by the community. Pre-publication or post-publication. And social media are informal nowadays. Everybody has a Twitter and Instagram accounts, and when papers are published, everybody is putting this on social media, and people start to respond. So the traditional process of peer review is currently changing. It's in flux, and we don't have the last word, but basically this is a response to what I'll present in a few minutes about the replication crisis and about the admission that the peer review doesn't really work well, and we need to do something better. So here I'm just giving some citations. Most of the citations will be from previous years when I prepared those slides. Here you see a trial of new peer review by the journal Nature. Trial of transparent peer review yields promising results. Last year, nearly half of Nature authors agreed to publish anonymous referee reports. We hope that more will consider doing this year. So even the most famous journals like Science and Nature are experimenting all the time in trying to improve the peer review process. Here is another example. This is Nature Method. Register reports at Nature Method. Nature Method is introducing a new article format, register reports. We encourage all authors interested in submitting comparative analysis of the performance of established related tools or methods to familiarize themselves with this alternative approach to peer review. So again, the paper, basically you submit and the paper is going to be published and the review basically will come only later. They call this new format registered reports. Here is another example from eLife, peer review without gatekeeping. eLife is changing its editorial process to emphasize public reviews and assessments of preprints by eliminating accept-reject decisions after peer review. So as you can see, all the journals are actually struggling nowadays in trying to make this process better, recognizing that the traditional peer review is not working well. Most significantly is the emphasis placed on directing papers into journals has turned journal names into the de facto currency of academic research careers and institutionalized the practice of judging scientists based on where rather than what they publish. This has in turn transformed journals from means of communicating science into gatekeepers whose judgment, ones that are heavily influenced by bias, fetishness, and chance, can determine which science get seen and which scientists succeed. So, you are all familiar with the concept that if a department wants to hire a new young professor, they will ask how many Science and Nature paper he has published. So the currency is how many, papers in good journals you have published. And who gets to decide this? The editors and the reviewer of those journals. And they might have biases and they, accept papers from very established good groups, but reject papers from unknown authors or third world countries and so on. So it becomes an exclusive group of scientists that promote themselves, and it's very hard to penetrate this group. There is a lot of criticism nowadays about this process. As we said before, people are judged by how many papers in good journals they have, by their age factor and so on, and really not by the quality of the work that they've published. Authors should be able to share their work freely and openly when they think it is ready. Peer review should consist of scientists publicly sharing their assessments of already published papers, either under the auspices of an editorial organization that oversees the review process or on their own. So this is really called for changing the method. And basically the idea is that the whole community judges the quality of your work and not particular sets of editors and reviewers, because those most likely have biases. Work of science should be reviewed by multiple relevant groups and individuals throughout their useful lifespan. And the biggest change we are making now is that we will no longer make accept-reject decision, follow peer review, nor obviously ask our reviewers to make publishing recommendation. So this is a pretty big deviations of eLife. eLife, as you might know, was the very first open science journal, starting in Berkeley. And here they come and say peer review is not working and we are going to change it.
Can I ask a question, please?
Of course.
So
go ahead.
This method looks great, but it may open like a gate for publishing nonsense research. How can this method prevent it?
Well, the concept is that whatever is nonsense over time will be proved to be nonsense. If you can post, your comments on a paper over and over, many years, eventually you will know that this is nonsense and it's wrong.
I see. Like evolution.
Yeah.
Evolution, like
the review is built over time rather than, given a set of, 2 or 3 scientists from very well-known universities who are very established, and they decide if your paper is good or not. The idea is that you let the whole public decide if it's good or not, and it will take time. It's not immediate.
Okay.
Also, we do not have the capacity to review every preprint submitted to us. We will publish every paper we send out for review as reviewed preprint, a journal style. Paper containing the author's manuscript, the e-life assessment, and the individual public peer review. The authors will also be able to include a response to the reviewers and assessment. So basically, you open up not only the paper for everybody to comment on over time, but you give a chance for the authors to also respond to the criticism. So it's basically a whole document. You have the original paper, and then there is a whole discussion happening. And eventually, years later, you can come read the original paper, the comments, and the responses of the authors. And eventually, history will judge if this is good in important contribution or not. Okay, so we covered so far the scientific method and the peer review. And now I would like to draw your attention to the failure of the scientific method as we experience it nowadays. Any questions so far before I move to the next topic?
Yeah, I wanted to ask about, you mentioned meta-science. What method do we have, or unless you're gonna get to this later, what method do we have to review science? If science in itself, let's say, has a flaw, wouldn't any flaw in science thereby lead to a flaw in
All right,
research of science?
so this is very good. This is the last bullet. That's a beyond open science. Can you save this question for then? Other questions? All right. So most of the credit goes to this guy, John Ionides, who started to bug the whole scientific community since 2005. And it took him about 10 years to get some traction for people to listen to him. Here he comes in 2005 with an essay where the title of this essay is "Why Most Published Research Findings Are False." Pretty provocative. And, he keeps on doing this for a long time. Here is a commentary in the Atlantic from 2010. Lies, damn lies, and medical science. Much of what medical researchers conclude in their studies is misleading, exaggerated, or flat out wrong. So why are doctors, to a striking extent, still drawing upon misinformation in their everyday practice? Dr. John Ionides has spent his career challenging his peers by exposing their bad science. Here's another paper from John in 2012, Why Science is Not Necessarily Self-Correcting. History suggests that major catastrophes in scientific credibility are unfortunately possible, and the argument that it's obvious that progress is made is weak. Efficient and unbiased replication mechanisms are essential for maintaining high level of scientific credibility. In the absence of replication effort, one is left with unconfirmed genuine discoveries and unchallenged fallacies. So this is really a crusade of one person over a period of almost a decade saying, guys, we are wrong. We are not doing science correctly. And there are many examples for this. And in order to improve our science, we need to show that we can replicate results. In several fields of investigation, including many areas of psychological science, perpetuated and unchallenged fallacies may comprise a majority of circulating evidence. Yet another paper by the same guy, 2015. failure to replicate. Sound the alarm. Science has always relied on reproducibility to build confidence in experimental results. Now, the most comprehensive investigation ever done about the rate and predictors of reproducibility in social and cognitive science has found that regardless of the analytic method or criteria used, fewer than half of the original findings were successfully replicated. While a failure to reproduce does not necessarily mean the original report was incorrect, the results suggest that more rigorous methods are long overdue. This is PLOS Medicine, 2016. Why most clinical research is not useful. As a result of decades of those alarming papers and conferences and basically discussing that things are not working well, NIH started to listen to John. And in particular, there was a claim that many papers relate to cancer in cell biology, molecular biology, where people publish all kinds of results, are not reproducible. And NIH started to pay attention and established something called the Replication Project in cancer. So here is 2016, cancer research is broken. There is a replication crisis in biomedicine, and no one even knows how deep it runs. So eLife, the journal that is dealing with open science and was the first to change the review process, in 2017 announces a project, Reproducibility in Cancer Biology, the Challenges of Replication. And basically a competition is basically announced, and NIH is funding this. And people are going to try to repeat very, very, very famous results over a period of 50 years of all the most important and most highly cited papers in cancer biology. So they announced this challenge, and already in 2017, interpreting the first results from a reproducibility project, cancer biology requires a high nuanced approach. The aim of the reproducibility project, cancer biology, which is a collaboration between the Center of Open Science and Science Exchange, is twofold: to provide evidence about reproducibility in preclinical cancer research, and to identify the factors that influence reproducibility more generally. And here is an interim result. This is 2017. Already things don't look good. They are trying to replicate famous papers, and reproducibility project yields muddy results. An ambitious effort to replicate cancer studies is provoking controversy. This is ANBO reports 2017, again pointing to the crisis. The assertion that 50% level of reproducibility equates to a crisis, or that many of the original studies were really fruitless, has been disputed by some specialists in replication. So there are two camps: the camp that says things are wrong, everything is broken, we have to start all over again, and the other camp saying, well, it's not as bad as we think, and many of the original results are okay. So here is the NIH challenge: plan to replicate 50 high-impact cancer papers, shrink to 18. So in 2018, the project was announced. They said they are going to replicate results from 50 papers. And in 2018, so well, we cannot do this. We are going to try to do this only for 18 papers. And many reasons, because in the old days, materials and methods section for each paper was not detailed enough. Lab notebooks of the original researchers are not available anymore because those are very old papers. People died, whatever, materials disappeared. Cell lines are not the same cell lines and so on. So they come to the conclusion they cannot really replicate. They reduce the number of papers to 18. In December 2021, eLife published the results of this project. There are 2 papers published back to back from the same group of authors. And those are summarizing the attempt of reproducing those now 18 papers rather than 50. I'm not going to read all this abstract, it's too long, but basically conclusion, challenges for assessing replicability in preclinical cancer biology. That's the title of one paper. This next one is actually is very quantifiable. They're already giving some statistics on what could be reproduced and not, and what could not. And the following week, all the journals that relate to biology report on the results that were published in eLife. So here you see commentaries in Science, in Nature. Disappointing numbers. Out of 53 prominent preclinical cancer papers, only 23 could be put to the test, and many did not have clearly reproduced results. Lack of rigor is often blamed on pressure to publish, but ethnographers can find out what truly keeps science from upping its game. More barriers to reproducing preclinical results include unhelpful author communication. A high-profile replication study in cancer biology has had disappointing results. Scientists must reproduce their efforts to find out why. So basically, the result of those 2 papers in 2021 published in eLife is we cannot reproduce. And if you open the most famous biology textbooks, they cite those important papers. So that's a crisis, a real crisis. Just another example why things are going so wrong. You are all physicists. How many of you are doing some biology-related work, and if any, biophysics? Nothing. So for doing any cell biology work, one needs to keep cultures of cells in the lab. Basically, you have incubators, you freeze cell lines in helium temperatures, you thaw them, you give them food, and the food basically is blood from cows. You go to slaughterhouse and you extract serum and you sell this serum, and each batch is different because you're taking it from individual different cows. Even if you take a batch and you mix everything and so on, from batch to batch, the serum is not identical. You grow those cells, and if there are different factors in each batch, you get different biological phenomena. This is one example why it's very hard to reproduce things. So think about going to a molecular beam epitaxy machine and making quantum well structure or 2D graphene or whatever, and each time you get slightly different samples. So your exosomes are going to behave differently each time you do an experiment. So the replication crisis is something we now recognize, and there is a lot of publication relating to it, but it obviously tells us that the way we have been doing science, especially biology and psychology, over many, many decades is not good enough. Now think about AI. Artificial intelligence faces reproducibility crisis. So once you build neural nets and you're changing hardware and you're changing algorithms, and you can imagine that you'll have the same crisis there too. Unpublished code and sensitivity to training conditions make many claims hard to verify. Think about basically the digital archive of everything that we do, writing codes in old languages, on old hardware, losing the codes, trying to reproduce things, computational challenge their scientists to revive and run their own decades-old code. So scientific results published with old codes on old machines, can we reproduce it with new codes on new machines? Is AI fueling a reproducibility crisis in science. Data leakage threatens the reliability of machine learning used across disciplines, researchers want. So it's not only psychology and medicine, it's actually all over, and we are probably going to face a new replication crisis, is basically computations based on AI. So to summarize this chapter, the replication crisis as of 2020, an ongoing methodological crisis in which it has been found that many scientific studies are difficult or impossible to replicate or reproduce. The replication crisis affects the social sciences and medicine more severely. The crisis has long-standing roots. The phrase was coined in the early 2010 as part of growing awareness of the problem. The replication crisis represents an important body of research in the field of meta-science. And because the reproducibility of experimental results is an essential part of the scientific method, the inability to replicate the studies of others has potentially grave consequences for many fields of science in which significant theories are grounded on unreproducible experimental work. The replication crisis has been particularly widely discussed in the field of psychology and medicine, where a number of efforts have been made to reinvestigate classical results to determine both the reliability of the results and, if found to be unreliable, the reasons for the failure of replication. All right, so let's ask you another question. What are the causes for the replication crisis? Changing conditions, very old study. Nature is random. Inaccuracy. Many AI. Nature of research. All right, thank you. Let's move on. So what are the causes? Publication bias and selection bias, generation of new data, publication at an unprecedented rate. We are really experiencing exponential growth of scientific output since the development of the personal computer and all the computation tools that we have. It's very easy to publish new papers, cut and paste and build new papers and use AI. And so more and more students want to get PhD. China is big in the game, and now we have a huge amount of scientists who want to publish. And how do we make sure that the quality of all these papers is good? So we get a lot of crap published, basically. Majority of these discoveries will not stand the test of time. Failure to adhere to good scientific practice and the desperation to publish or perish. Really, the incentive is to publish, not to do good science. We have to change the incentives for the whole system, such that you are rewarded for producing good science rather than you're rewarded for publishing more papers in Science and Nature. Multiple varied stakeholders. Basically, the journals are making money off you publishing papers, and their motivation is money. Again, not necessarily the best science.
Yeah,
So what are the responses? Yes, there was a question.
Yeah. How can we know if the ones that are redoing the experiment are doing it good enough to check? Maybe they are just not good enough.
So for that project, there were rules, very specific rules, how to reproduce and so on. Obviously, you need to go to old papers that there is enough information that allows you to reproduce the paper, that you can get the exact same lines, that you get the same reagents, that you're really the protocols that are written, how many minutes, at what temperature, whatever, all that stuff is there that you can go and try to reproduce. In biology, it's much harder than in physics. So this is why they were not able to reproduce 50 papers that they wanted, but much fewer. And even then, the lab notebooks, so the authors were not good enough. They were not online. And you know, this is why the whole industry is changing. Now, when we write a paper, we put the raw data, not the analyzed data, but the raw data in depository. We write a detailed protocol and we publish the protocol. So we are trying to do better. And the journals are now asking much more from authors than they used to, especially in life science journals. You are required to put so much stuff online such that other people can try to reproduce what you've done. This is essential, but I can give you many examples from physics as recently as a few weeks ago about the high temperature room temperature superconductivity. I hope that one of you picked this example up for presentation. People come with all kinds of claims, and then other people try to reduce and cannot get it. So here is a replication crisis. The reason could be fraudulent science, not necessarily, mistakes, but it's happening all the time.
Yes,
all right,
thank you.
So what is the response? The replication crisis, what are the responses? So we mentioned this word meta-science, we'll define it in a second. Tackling publication bias with peer registration of studies. So basically, we said that journals prefer to publish, let's say, papers from Harvard, Columbia, Yale, whatever, than from a remote college that you don't know the name. It's well-established scientists have easier time to publish the paper in top journals than not established scientists and so on. So in order to remove that bias, you want pre-registration of studies. So basically you're saying, I'm going to publish a paper about this and this, and therefore this is my declaration, and then you submit the paper. So trying to eliminate the biases. Shift to a complex system paradigm, basically saying life is not simple, it's complicated. Emphasizing replication attempts in teaching. We want to train new generation of students that know about the crisis and they are well aware of this. And when they start, they are doing experiments or simulation or whatever, they basically design their PhD research plan or the paper or whatever already with this crisis in mind, so that they can give answers. Reducing the p-value required for claiming significance for new results. So especially in psychology, there is a lot of use of statistical tools where the psychologists themselves are not experts on probability. And so how to use p-value, educate people how to use p-value. Addressing the misinterpretation of p-values. Encouraging larger sample size. When I was a young postdoc in AT&T Bell Laboratories, it was enough to make one wafer on a molecular beam epitaxy machine, go to the spectroscopic setup you had, put your sample in, do one low temperature measurement and publish in physical review letters. There was no replication efforts whatsoever. we tend to think that in solid state physics, if you have a sample, you have the same laser or whatever, you always get the same results. But in physics, it wasn't really an issue of trying to do control experiments, repeat the experiment many times, and have some statistical meaning for what you do. Nowadays, it's changing, but when I was a student, that was just biology that had these issues. Physics never had this issue because people did not try to replicate. Sharing raw data in online repositories. So now it's a requirement to put your raw data that you publish and analyze the results and publish them. Put also the raw data somebody else can actually analyze and maybe find that you have a mistake in your analysis algorithm. The funding agencies are now putting money to do application studies. Emphasize triangulation, not just verification. Basically, we draw conclusion not only from one set of experiments, but several. Raise the overall standards of method presentation. And the biggest really response is what we call nowadays open science, open access, open data, open analysis code, electronic laboratory notebooks, and so on. So nowadays you are required not only to put your raw data on depositories, but actually the code you've used and you've written for the analysis and so on. So all of that needs to be out and public, and people can test you on each step of your work. You can reproduce experiment, they can reproduce the analysis and so on, and check everything that you've done. I'm trying to. All right. So basically, we require for every published work to have enough information that anybody who wants to can replicate. All right, so that was the work for today. We'll talk a bit more about meta-science for next time. I would like to open now today's presentation for questions. I want to repeat what I said at the beginning, what expectation from you for this course. First is to attend, and then we will have you answer one homework problem, and then you pick up a paper mostly about misconduct in science, and you'll both write a 2-page PDF on that paper, and you'll present for about 25 minutes in English, a PowerPoint presentation where you are basically taking my role. I think we have 12 students in this course. We are going to have 4 last meetings. So that means 3 people represent on each day of those last 4 classes. So think already about, and you can talk to me, think about what you want to present, start to look for interesting stories, and pick up a date. Next time we'll probably set up a calendar, but we cannot accommodate more than 3 per session. So think about the last 4 lectures in this semester, pick up a date, pick up a topic, and talk to me. Any questions?
Yeah, can we just, about my question on meta science, is that relevant to this lecture or next one?
Yeah, well, we'll cover this, but yes, the response is to do science on science. Basically, you use a scientific method to ask questions about, is your science good or not good? And what do you need to do so you can come up with hypotheses? So meta science really requires a lot of information about the scientific endeavor, and then you use statistical tools to try to withdraw some information, how bad things are good, or how to improve. It's a discipline in flux. It's not really well defined, but we'll talk about this at the beginning of next meeting. More questions? All right. If not, I wish you all good night and looking forward to spending the next 2.5 months with you. All right. Good night. Laila tov.
Thank you.
Good night.
טוב, שמעון, אמרת לי להישאר אחרי ההרצאה.
כן.
בשנייה. אין לי בעיה לדבר אם יש פה עוד אנשים, זה בסדר.
דניאל, אתה יכול לרדת מה... אוקיי. דניאל? אוקיי.
היי.
אוקיי.
אז
אז אמרת שאת לא יכולה להיות בכל השיעורים, נכון?
לא בהכל, בשניים.
בשניים.
כן,
אז
שאחד זה בעצם
מה התאריכים?
הערב, אני אגיד לך, אחד זה הערב של החינה, שזה כמו אירוסין אצלנו, זה יוצא ב-28
אני
לחמישי.
יודע מה זה חנה.
לא יודעת מי יודע, מי לא יודע. אז אחד זה ב-28, והחתונה היא בשני.
28 במה? ביוני?
במאי. בחודש
אותו.
הזה. כן, זה ממש בבית.
אוקיי, זה תהיה הרצאה שלי, כן, ואחד.
ואחד בדיוק שבוע לאחר מכן, כי החתונה היא ב2/6. אז
עוד פעם מזל טוב. אוקיי, אז תראי, בעיקרון אני שם על הלומדה את הפאורפוינט, בפורמט כזה יותר צפוף, זה 6 סליידס פר פייג' וכן הלאה, ואת ההקלטה של הזום.
אוקיי.
אז מה שאני מבקש מהם, פשוט לעבור על מה שאנחנו עברנו בכיתה, בסדר?
בסדר גמור.
וכמובן לעמוד בכל המטלות של הקורס.
כן, ראיתי את התאריכים, הם יהיו בסדר גמור, כאילו אני אסתדר.
והרבה מזל טוב.
תודה רבה.
יופי.
תודה רבה.
שיהיה בהרבה הצלחה.
תודה רבה. להתראות.
אוקיי, לילה טוב.
ביי, לילה טוב.